Good day, trainees. Welcome to the video of module 9. From now on, we'll deal with polygon of forces. Now we are going to deal with 3 or more forces that are in equilibrium. I hope you have gone through all the previous videos because we are still dealing with forces, and we are going to relate a lot to the previous work that we have covered. Now, a polygon is a shape that has 3 or more sides, and the sides are straight, and it's a closed shape. So this means if a shape is curved, have curved sides, it's not a polygon. If the shape has 3 or more sides but it's not closed, then it's not a polygon. So a polygon is a shape with 3 or more sides, straight sides, and it's closed. And this is the shape we are going to deal with because our forces are said to be in equilibrium. Now, how do we describe polygon of forces? Now, the definition of polygon of forces, we say if more than 3 coplanar forces are acting on a point and they are in equilibrium, they can be represented in size and direction by sides of a closed polygon when taken in order. It can also be 3 forces. So it's 3 or more forces. They are said to be in equilibrium, and then we'll represent their size and direction by a closed polygon. In triangle of forces, remember we represented the forces using a triangle. So this time around we are using a closed polygon. Now we use the both notation, the one we did in triangle of forces. So these two are related, and we are going to join our forces head to tail. That is the same method as in the triangle of forces, and it is what we'll apply here. Head to tail, meaning our arrows will be following each other, our forces will follow each other, and we'll join them in an orderly manner, either moving clockwise or anti-clockwise. It depends on which either order you are comfortable with. Now let's get to the real business of drawing our polygon of forces. But before we do that, I quickly want to explain to you our directions. How do we represent the directions of our forces? I want to quickly emphasize that. Angles and direction of our forces. As we know, we have 4 main directions: north, east, south, and west. Those are our 4 main directions. And then we have directions that are 45 degrees away from the main directions. These are the directions: the northeast, southeast, southwest, and northwest. Those directions are specifically 45 degrees away from the main directions. Then we have other directions that are between the secondary directions and the main directions. For example, northwest, north, northeast, and all those types of things. They are between the main directions and the secondary directions. So when we represent our forces, if a force is not the main direction or the secondary direction, it means we have to give the directions, and then we must put an angle between the 2 directions between which that certain force lies. So if you look at 17 newtons, for example, you will see 17 newtons is a force moving in the westerly direction. If you look at 25 newtons, 25 newtons is a force that is moving northeast. That we can write them 17 newtons west or 25 newtons northeast. we can write them that way. But what about 5 newtons and 10 newtons? How do we write them? How do we represent the directions of such forces, where we are only given an angle that is not 45 and it's not 90? Now look at this. I've written down the force sizes and their specific directions. 17 newtons is moving in the west direction, 25 northeast. 5 newtons, if you look at 5 newtons, you will see that between east and 5 newtons there is an angle of 20 degrees. So this means that between south and 5 newtons there is 70 newtons, because it's 90 minus 20 degrees. Now we can represent 5 newtons using two directions. We can either say, if you move from the east going to the south, you will move 20 degrees to come to 5 newtons. But if you are moving from the south and you are headed to the east, it means you will move 70 degrees to come to 5 newtons. The same thing applies for 10 newtons. 10 newtons, if you are moving west, you move 75 degrees to the south. If you move south, from the south, you will move 15 degrees there, and then you will come to 10 newtons. That's when you move south to west. So in that case, that is how we represent directions such as directions of forces such as 5 newtons and 10 newtons. It's very important that you know how to represent your directions, because when we are drawing our polygon of forces, we are determining the resultant in the equilibrium or the unknown forces, and we need to exactly know how to represent our directions, how to write them down. It's very important, so make sure you go through them very thoroughly and understand them before you watch the part of drawing. So let me take you along and let's draw our polygon of forces. I will do 3 or 4 examples, and after that I will leave you with an exercise, and please do as much practice as you can of drawing your forces. In this way you can improve your accuracy, and then the way of how your accuracy and how you use your drawing equipment. You need to be very accurate when you draw your forces. Okay, now we have come to the part where we are going to determine our unknown forces, our resultant, and our equilibrium. Now example A says, determine the size of the unknown forces L and M. This is what we call your space diagram, and we are going to draw our vector diagram or our force diagram just below the space diagram. Remember, a vector diagram is to scale, and we have discussed our scales in the previous videos. So the scale that we are going to use, you can either say 10 newtons equals to 10 millimeters, 1 newton equals to 1 millimeter, and then 10 newtons can be equals to 1 centimeter. Those are the common scales that we use. Now you are given 4 forces, and you need to determine graphically the missing forces that is L, and force M. Those are the forces that are missing. So I'm going to take you step by step how we are going to draw our diagram. The first thing that you need to do is to determine which force am I comfortable to start with. In this case, the force 80 newtons, and remember you start with a known force, is the one that is comfortable to start with, and it's also the force between the last unknown and the first known. So A will be here. Remember Bow's notation. So that is how we are going to letter our diagram, meaning we are going to start with line AB, and line AB is 80 newtons. Okay, I hope you have selected your suitable scale and you have made a note of your space diagram. If not, refer to your textbook on page 107. This is where this example is taken from page 107. We have our example there, so you can refer to the space diagram there. Now let's start drawing our vector diagram. Remember, you need to have enough space to draw your diagram. So we can first make a simple shape of how our diagram will look like. As we say, we are going to start with 80 newtons. That is 80 newtons. And then we are going to bring in 50 newtons. Our M will be there. And then our L will be there. That is the shape of our diagram if we start with 80 newtons, meaning we need to have enough space on this side. So I am going to start drawing. I start with my 80. Start with my 80 newtons. The next force that I'm going to draw is 50 newtons. And 50 newtons from the reference line. This is my reference line, the west east line. On the west east line, this is the line I use as my reference line. You will see that 50 newtons is 30 degrees from the reference line. So I take my protractor and then I measure sorry for this protractor, I'm just quickly going to change protractors. Okay, I'll measure 30 degrees. If you are measuring on the inside, it means it will be, on the inside it will be 150, but from the outside you will measure 30 degrees. Now you will see that my space here is not enough, so I'll just delete this and then I'll start a bit on the inside because I don't have enough space to draw. So let's say I'll draw it here. Okay, then draw my 80 newtons. This is my line for 80 newtons. Then I will measure 30 degrees. Then I will draw my 50 Newton line up to there. On your 50 Newton line, at the top there, you can draw a reference line, a dotted line. Please do not extend your 50 Newton line. I use a reference line, a dotted line, so that I'll be able to measure my angle here. My angle there is 30 for L, and if you see here, if we go back down there, you will see I measured an angle of 30 degrees that is indicated on your space diagram. You do not change the angles of the forces, and then you do not change the direction of the forces. You also do not change the sizes of the forces. You keep them as they are on the space diagram. If you take them in an orderly manner, you will get to the right answer. Now, if you look there, our L is 30 newtons from the reference line. So I place my protractor there, and then I measure 30 degrees. I draw a line of L. My line of L is unknown, my size of L. So I'll just draw a line that will meet with the line of N. A long line, and remember M must start from here. M is a line, it's a vertical line. So you just place your set square or your ruler at the end of at the starting point, and then you draw your line M that will stop in line L. So this is your diagram. I hope you can see it clearly. So all you need to do here is to measure M and L. Please label your diagram. Very, very important. Label your diagram, especially the sizes of the forces and your directions. So if we measure our L, this is a short ruler, it's this one. If we measure our L, for my L I got 14.1. If I multiply by 10, that will give me an answer of 141 newtons. If you look in your textbook, you'll see that the exact answer is 142, and remember your answers must be plus, minus 1. That is the range of your answer. And if I measure M, My M gives me 95 Newton. So if you have answers that are within the range of plus minus 1, then your drawing was accurate. And we move on to the next example. Right, I took my next example, example B, from page 110. It has 5 forces. I'm sure by now you feel that it's more complicated, but it's not really complicated as long as you know your principles and the basics of drawing and how you join your forces. It's very, very easy. And if you look, you can see that they've shown that they're starting with AB. We can start with AB. AB is a force of 30 newtons, and like I told you, it's comfortable if you start with forces that are either horizontal or vertical. You can also start with the 30 newtons that is horizontal, and then you move from there. The force that you start with is not concrete. You can choose to start with any of the forces, but it's more advisable to start with a vertical or a horizontal force if there are any of them that are, if there are any in the system of forces. So we are going to start with the 30 newtons that is vertical, and we are going to draw our vector diagram. I'll be using a scale. I use centimeters. My rulers have centimeters. All of them that I have centimeters, so I use the centimeter scale. 10 newtons is equals to 1 centimeter. Make sure your space diagram is visible when you are drawing your vector diagram, because you are referring to it. Just don't copy what I'm doing, but make sure you are referring back to your space diagram. Alright, let's start drawing. We said we are going to start with the 30 newtons, the vertical 30 newtons. I'm just going to start somewhere here below. 30 newtons. That will be 3, the centimeter ruler, the centimeter scale, sorry, 30 newtons. The next force that you are going to draw is 40 newtons, and you will see that 40 newtons is 45 degrees from your reference line. Like I said, I prefer to use a reference line. I just draw a dotted line there on top, and then I measure 45 degrees. Then I draw the 40 Newton force. So I draw a reference dotted line, and then I measure my angle of 45, and then I draw my 40 Newton force. The next force that you are going to draw, is a 30 Newton. And then if you see, they said the 30 Newton is horizontal. So you come at the top of your 40 Newton force, make sure your ruler is straight, very straight, and then you draw your 30 Newton line. Newton. Now we can use 30 Newton as a reference line, and then you will see that the next force that we have to draw is a 30 Newton again, and it's 45 degrees from the reference line. So this is my 45 degrees here, and I draw the 30 Newton line just there. Then you can make a dotted line again for reference, so that you draw your last force. Your last force is a 30 Newton, and it's 60 newtons. You see its angle that is indicated is 60 degrees from the reference line, and that force is 30 newtons. 3. So that is 30 newtons. Remember, we are solving for the equilibrium and the resultant. That means your resultant will be here. You see, because we need to close up our polygon since our forces are in equilibrium. So our resultant will be there. We can indicate it with a dotted line. Now, at the beginning or at your start, you must indicate your directions, your 4 main directions must be indicated there, so you can correctly determine your angle of the resultant. The direction of the resultant will face there, in the direction of the equilibrium is there. So this side is E, equilibrium, and here is R. Now you measure the size of your resultant in your equilibrium and their angles. So the resultant the size that I got is 67. That is the same size for 67 newtons. Remember, they are equal in size but in different directions. Now there are 2 angles that you can use. You can either use that angle or that one. For the equilibrium, you can use that angle or that one. Those are your angles that we can use. Remember, when I was explaining the directions, I showed you how you can represent the the directions of your forces. Now let's measure the smallest angle here from the east to the resultant. I have that if I move from the east, I'll need to move 10 degrees. My smallest angle here is 10 degrees going to the north. And that means that this is the same angle here for the equilibrium, and it will be west 10 degrees to the south. If you use the other set of angles, it means you will say, if I'm moving from the north, I'll move 80 degrees to the east for the resultant. For the equilibrium, it will be south 80 degrees to the west. So those are the two answers. Now, if you look at this diagram, you will see that the area of the resultant is facing the last area or the last first. I want to explain to you why is the arrow of the resultant facing the last arrow and why is the equilibrium in the opposite direction. So I want to explain this whole setup here, why we have our directions at the starting point. I want to explain that to you before I give you an exercise to do. So I'm going to explain to you the whole concept behind the polygon of forces and how we get to our answer in the directions and why the arrow is facing which side. Now imagine you have this table in a room at home. Now you want the table to come here. At this spot, or let's say in the end the table must come here. That is the spot where you want the table to be, and you are moving the table from here. That is where you are moving your table from. Now you start moving your table. Now look at what I'm doing. So you move your table that direction, then you stop, then you decide, no, I don't want my table to be there, I want it to be somewhere else. So that was your first movement. You pulled or pushed the table and then you stopped there. So that was your first point, your first stop. Then you continue and you pull your table like that. You see, now you are going in that direction, so you change your direction, and then now you are moving your table like that. So let's say you changed your direction with 45 degrees and you stopped there. So this is your next stop. Then you decide, no, I want my table to come here. So you move it, you change direction, and then you move like this. in this moment in time, you are here. You have changed your direction again. Let's say 50 degrees. You changed direction and now you are here. Remember, you are moving a table to the spot from point 1 to point 2. Then you'll see, aha, finally I can move straight and my table will be in the position where I want it to be. These are forces. Let's say it's 5 newtons, 7 newtons, 12 newtons, and 11 newtons. So these are the forces that you used in the direction that you moved to bring your table there. So now that your table is in place, you are happy. So let's say if you didn't move, take all those steps, make all those movements, 1 2 3 4, you could have just, if you knew exactly where you wanted your table to be, you would say, I will move my table from here and I will bring it there. See what I mean? So you will move your table only with one movement. And then you bring it. So this is the force we are saying is our resultant. This is our resultant force. It will replace all the other forces and you will only move once. So that is why I said you put your 4 directions here to determine your angle or the directions. You see, and that is why you see that your arrow of your resultant will face the last arrow. So this is your resultant or the replacing force that will replace all those 4 forces. And if you say, let's say you are in class and one learner wants to move the table from here to there, you are in class, but the other one says, no, this is my table, please do not move it. The other one decides the table will remain here because it's mine, I must sit on it. So the second learner opposes the first learner and tries to pull this table in that direction. So this is your equilibrium force that will allow this table to remain in position or to remain balanced. And this is how we determine our angles, either that one or this one for your resultant, and then that angle or that one for your equilibrium. So if one student applies an equal force on this side, that table will remain in position. I hope you get the concept of polygon of forces. Now in your textbooks you are going to do self-assessment 1, you must do the practice of number 1, A, B, and C, and you must also do the practice of number 2. There is A and B. After the video, I will upload the diagrams of the self-assessment 1, number 1 and 2. Please make sure you practice your drawing of polygon of forces. Thank you for watching.